You are welcome to our lesson on landing dispersion forces. In order to understand what landing dispersion forces are, or what landing dispersion forces, the first thing we need to understand is what temporal dipole is. In an earlier lesson, we discussed permanent dipole when we were looking at dipole-dipole interaction. So if you want to review that lesson, or you have not watched it yet, you want to watch, you can check the link under the description. Or better still, you can check our playlist of organic chemistry and have access to that video. So what exactly is temporal dipole? What they say?
So temporal dipole is the momentary and even distribution of electrons in an atom or molecule.
Good. So the main thing we want you to pay attention to is the fact that temporal dipole has to do with on a momentary uneven distribution. It is momentary, unlike permanent. So we'll use this to represent an atom. So we'll use this to represent a model of an atom, and then with this we'll understand what a temporal dipole is. So let's see how this distribution occurs.
So it occurs when electrons in an atom or molecule randomly shift or move to one side more than the other.
Good. So that's how temporal dipole comes about. Electrons are constantly moving. So if you look at the model of the atom that we have on the screen, you can see that the electrons in this atom are evenly arranged. They are evenly arranged. But electrons are constantly moving in the atom. So at one point in time, you will see that all the electrons tend to move more and become clustered at one side than the other. So they have been shifted to one side more than the other. And as a result, the side that has less electron becomes electron deficient. What about the side that has more electron?
It becomes electron rich.
It becomes electron rich. So the electron deficient side is partially positive, and the electron rich side is what?
Partially negative.
So at this point in time, we will say that this atom becomes a dipole because it has two poles, a partially positive side and a partially negative side. But what kind of dipole is it? It is a temporal dipole. So this is a temporal dipole because the electrons can become evenly distributed again. The electrons can become what? Evenly distributed again. How? Look at this temporal dipole can revert back to even distribution of the electrons. And then these evenly distributed electrons in the atom can revert back to a temporal dipole state again. So that is why we say that this kind of dipole is a temporal dipole. I think that makes sense and it's simple to understand. Is that also?
Yeah.
So now that we understand what a temporal dipole is, we can move on to understand the next thing we need to clear in order to explain what landing dispersion forces. That is induced dipole. But before we explain what induced dipole is, let's recap on temporal dipole. Remember we said the electrons are evenly distributed, right? But at some point in time, they become shifted to one side more than the other.
Yeah.
And as a result, the one side becomes partially positive, while the other becomes partially negative. The side that is partially positive is the side that is electron deficient. What about the side that is partially negative? It is what?
That one is electron rich.
It is electron rich. It is rich in electron. So this kind of dipole is known as a temporal dipole. So now what do we mean by induced dipole? Let's take the definition before I go on with the explanation. So what is induced dipole?
Induced dipole is a temporal dipole created in a nonpolar atom or molecule when a nearby charged particle or dipole distorts its electron cloud.
Good. So that's the definition of induced dipole. But let's say it's explain further for us. So it is a temporal dipole created in a nonpolar atom. So let's assume we bring a nonpolar atom close to the temporal dipole. It is nonpolar because the electrons are evenly distributed in this atom. But remember, the temporal dipole has a positively charged end and a negatively charged end. So this is what happens. The positively charged end of the temporal dipole will attract the electrons towards itself, because positive becomes attracted to negative. Electrons are negative, so the partially positive side of the temporal dipole draws the electrons in the nonpolar atom towards one side. So as a result, the once nonpolar atom becomes what? Polar, meaning it becomes a dipole. One side becomes partially positive and the other side becomes what? Partially negative, meaning it is now what? An induced dipole. Why is it induced dipole? Because of the meaning of the word induced, or in other words, it has been influenced to become a dipole. It has been influenced by the temporal dipole to become what? A dipole. So that's why it is called induced what?
Dipole.
Induced dipole. But suppose we bring another nonpolar atom close to this induced dipole. Now remember, this induced dipole also have a partially positive side. So this partially positive side, meaning that side is electron deficient, so it is partially positive. It will end up attracting or drawing all the electrons in the neutral or nonpolar atom towards one side, towards the partially positive side of the induced dipole. So look at what happens. So the electrons are attracted towards the partially positive side of the induced dipole. And as a result, the once nonpolar atom also becomes polar. One side becomes partially positive and another side becomes partially negative. So this is how come induced dipole is formed. So I think we understand what induced dipole is, right? So this atom also becomes an induced dipole. So now, an attractive force is generated between the partially positive and partially negative atoms. There's some kind of attractive force because the partially negative and partially positive are side by side. So that attractive force that is generated between the partially positive and partially negative side is what is known as a London dispersion force. And it has a nickname, London dispersion force, or what?
It's also called induced dipole force.
Good. So the nickname, that is induced dipole force, actually describe the type of force going on. Because you can see that the atoms are induced dipoles. So the force between them is induced dipole force. So if you see induced dipole force, the same as what? London dispersion forces. Or simply put, some people say what? London dispersion. So that is a brief and interesting explanation of London dispersion force. So summary. So now let's summarize everything we've discussed so far. So in summary, what do we have?
So in summary, we've learned that electrons are constantly moving. So at any moment, an atom or a molecule might have more electrons on one side than the other. And this creates a temporal or instantaneous dipole, which can then induce a dipole in a neighboring atom or molecule, causing a weak attraction.
Good. Nice said. So this is all the essence of what you call the London dispersion force, also known as the induced dipole force. So points to keep in mind: electrons are constantly moving. So at some point they become saturated at one end than the other, and as a result you have a temporal dipole. And when you bring this dipole close to a nonpolar atom, it can induce or influence that non-polar atom to also become polar. And then the induced dipole can also induce another atom to become induced, or it can cause it to become polar. So the kind of attraction between these dipoles are what we know as what? Induced dipole force, or London dispersion force. So now let's look at some properties of London dispersion forces. What are some properties of London dispersion forces?
So these forces are the weakest of all intermolecular forces.
Good. Because so far we've discussed some intermolecular force already, that is dipole-dipole interaction. There is another one we haven't discussed, that is hydrogen bonding, which we'll be discussing right after this one. Among all of these intermolecular forces, the weakest is London dispersion force. So there's one point here. They say London dispersion force, or LDFs, are the weakest type of van der Waals forces. Van der Waals force is just the collective name for all these intermolecular forces we have discussed, and they are weaker than dipole-dipole and hydrogen bonding. What is the next property?
Then the London dispersion forces, they are also present in all molecules.
Good. All molecules, not only organic compounds. And the molecules they are present in, some examples appear on the screen. You have CH4, O2, N2, CO2. All of these depend on London dispersion forces as their only intermolecular force. So what that means is that there are some molecules that have other intermolecular force between them aside the London dispersion force. There we have the last property here.
The London dispersion forces, they are also caused by temporal dipoles.
Good. Remember, not caused by permanent, they are caused by temporal. But dipole-dipole interaction, which we discussed earlier, are caused by permanent dipoles. But London dispersion forces are caused by temporal dipoles. So this brings us to the end of this lesson. In our next lesson, we'll be discussing hydrogen bonding. So if you haven't subscribed to our channel yet, please do well to subscribe, like this video, and share the link with other students you know benefit from lessons like this. So what are we to expect on the hydrogen bonding? So we'll define what hydrogen bonding is. Then we'll explain how hydrogen bonding occurs in ethanol, explain lone pairs electrons, and then we'll look at some other compounds that also have hydrogen bonding. So subscribe to the channel so that you wouldn't miss our next video. See you.